Hi, everyone. So today we're going to go over time series models, specifically ARMA models. Now we know about models and linear regression and different clustering models and SVMs. We know about these regression and classification models. Today we're going to be taking a deeper dive into time series models, specifically ARMA models. So when we look at ARMA models, we know that there's two different components that make up ARMA. First is autoregressive and second is moving average. When we look at autoregressive, the entire purpose of an autoregressive model is that it's a model that uses the previous observations to make a future forecast. So you can see just from the model equation here that it's using the previous observations, and the number of observation that you're using, that's a parameter that you provide into the model. And we'll go deeper into how to actually get this parameter. You look at the partial autocorrelation function as well as the ACF. Um, but that's how we ultimately get the lag or the number of terms that we want to use, the number of how many previous observations we want to use to make our forecast. So that's the autoregressive portion. We use previous observations to make a forecast. The moving average uses, instead of the previous observations, it uses the previous errors, how far you were from the actual value, how far was your prediction from the actual observed value that occurred, and you use those errors to help make your forecast. So it's a linear relationship between the predicted y variable and the previous errors. And the number of errors is also a parameter that you use when creating this model, and how you get it is dependent upon the PACF and then the ACF partial autocorrelation function and autocorrelation function, identifying the lags, identifying the decay in lags, how sharply they're dropping off. That determines the order of both MA and autoregressive model and ARMA. And so those are the two main components as we discussed. Moving average relates the errors to the forecast. Autoregressive relates the previous observations to the forecast, and the number of terms, the number of lags that we want in each is dependent upon the PACF and ACF. One of the things about a ARMA model is that our data needs to be stationary, whether it's through Box-Cox transformation or through differencing. We want to make sure that we're stabilizing the mean and the variance. So when we have this time series plot where the trend is increasing, we can stabilize the mean through differencing methods. And when we realize that the variance is increasing, where there is a larger spread of the values as we increase the time component, if we realize that there's a larger spread in that, we're able to stabilize the variance through Box-Cox transformation. And the parameter that we use for that is lambda. How much do we want to stabilize the variance? But that is one of the pivotal components that we must make sure when we're running ARMA models is that our data must be stationary in the mean and stationarity in the variance. And because of this stationarity component, all ARMA models are all ARMA models and all ARMA models, autoregressive and moving average component, will always, in the long term, converge to the mean. And this is one of the properties that they have because we've assumed that the data is stationary. If the data is not stationary, then you have some different assumption and it's not going to converge to the mean. But when we have this assumption that the data is stationary, and that's this hard requirement that we have when running these ARMA models, is if the data is stationary over the long term, our forecast will eventually converge to the mean. And so this is one of the properties of ARMA models, is that it will always converge to the mean. And in fact, the variance of the error will approach some fixed value, some constant value. The variance of the error will approach some fixed or some constant value, which means that in the long term, how much our predictions vary will approach some fixed amount. And so that's one of the properties. And we've obviously discussed ARMA, AR component, autoregressive, moving average component. When we combine those two, that's our ARMA model. And then the parameters are referring to how much weight we want to give to each of the components within each of these two different models. So for AR, how much weight do we want to give to the last observation, the second observation, the third observation, and so on. For moving average, how much weight do we want to give to the last error, the second to last error, the third to last error? So the weights on how much we want to give to each of these errors and these previous observations, that's the parameters for both MA and AR. And obviously, when we run our model, when we do our predictions, our main goal is to make sure that our residuals are as close to white noise as possible. When they are close to white noise, that means that all of the patterns that we have supposedly modeled have been captured by the model that we have trained. There's no other systematic component that is left in the residuals after we've trained our model. Our model has done a pretty good job of capturing the trend, of capturing the systematic component after we've removed the trend and seasonality, because we are not trying to predict or model the trend and seasonality. That's a natural component of the data set. After we have removed the trend, after we've removed the seasonality, we're trying to model everything else that's remaining. Everything else that's remaining, that's what we're trying to model. And after we've modeled that, after we've seen that the residuals are as close to white noise as possible, that there's no other systematic component or patterns that are in the thing that's after the remaining of the model, our residuals, which is actual minus predicted, then we know that our model has done a good job. If there was some sort of trend, whether it was a quadratic trend or some relationship that you've seen within the residuals themselves that suggests that there is something left in the data set that is not captured by the model. There is some autocorrelate, maybe the residuals are highly autocorrelated, they're not normally distributed, they differ significantly from zero. If we observe that the residuals are not stationary, that are not close to white noise, and there are statistical tests that you can use to determine if they're close to white noise, but if we see that the residuals are not close to white noise, they're deviating from the mean of zero, etc., we know that one of the main reasons for this is that our model is not doing a good job of capturing the systematic components in the data set. And so that's when we go back, we adjust our model, we take a better look at the data, how we stabilize the mean, how we stabilize the variance. We try to fit a better model that's able to get residuals that are close to zero, normally distributed, and have little to no autocorrelation. So that's the goal. Now let's talk about exam FM. So three components to FM. First is if you're able to pass three back-to-back exams on coaching actuaries within around a week of the exam, that's going to put you in a good place to actually pass the original exam. If you're able to pass 24 out of 30 on coaching actuaries within 1 week of the exam under time conditions, you're going to put yourself in a good place of actually passing the exam. The second is that SOA questions definitely do come up, and I've even seen a couple direct questions from the SOA come up, like the SOA sample questions. So doing those will automatically help you get prepared. Like a couple questions were directly from the SOA sample questions. It's the wording of it, so that's going to help you. And then another thing that people sort of neglect is it's a multiple choice exam, so you want to take that to your advantage and plug in some of the answer choices. Some of the questions you realize you have to like do a lot of quadratic manipulation. Maybe it's a quadratic formula, maybe it's a fourth degree polynomial you're trying to solve, and a lot of times you realize that it's just much easier to simply plug in the answer choices and see which one works. And it might not be direct, but if you're looking for an I, if you're looking for the interest rate, plug in maybe V and then try to see if that matches to what you're trying to solve. But essentially use the answer choices to your advantage and know that the answer is within them and simply plug them in if it's a question that is necessitates solving this long quadratic formula or like solving this long polynomial equation. Next, let's talk about reinforcement learning. So we know that in reinforcement learning, we have this given agent that is trying to learn within the environment from the rewards that it's getting. It's getting feedback from the environment. It's trying to determine what state uh, to transition to by performing what action it's trying to get the optimal policy, what is a strategy to take in this environment. And so one of the ways that we can do that is through optimizing the value. And this is the equation. We refer to this as the Bellman equation. And so first we have what is the value of being in a particular state with n steps to go. So this value, you can think of this as what is the maximum expected reward. So this is both the immediate reward that you're getting after you do take a particular action, but then also the future discounted reward from the future states. And so this reward, this value, you can think of this as what is the worth or what is the reward that I'm getting, both immediate and long-term discounted future reward of being in this particular state. And the way that it does this is it takes the maximum of all of the values under all of the actions that you can possibly take. So, for example, if you're in state A and you have three different actions that you can choose from, it's going to take the maximum of the value that it calculates at state A, given you take this action, state A given you take another action, state A given you take another different action. So for three actions, given that state, it's going to calculate the value at each state action pair, and then the maximum of those is going to be your value at that state. And so how are we able to get the value at that state? Well, as we mentioned, it's the immediate reward plus the future reward. So the immediate reward we're able to get by the product of the reward matrix and the probability matrix. So that's the immediate reward. Now the future reward or the future discounted reward can be found by two things. One is the discount factor. So the discount factor is how much do you want to weight future rewards? Future rewards may not be as necessary. Do we want to provide some sort of discount factor to them, meaning that a reward of X maybe 5 time periods means something less now, right? So is there a time component to the rewards that we're getting in the future? And we're able to specify this through this discount factor. Then we want to see what is the future reward. Now, how can we get the future reward? Well, that is through summing all of the states that we can be at and multiplying the value of being at that state. Right? So it's the summation of the product of the probability of being at that next state times the value of being at that next state. So this entire Bellman equation is a recursive equation that we can use so that we know the immediate reward, that is the product of the reward matrix and the probability matrix. And then we know that the future reward is the product of the probability of getting to that state, given that you're already at state A and you take action A, and the value of being at that next state. And the sum of this across all of the states, across all of the possible states that you have, across all the possible states that you have, is your discounted future reward at that current state, given that you take a certain action. And then you do this for all of the different actions that you take. So just as a visualization, if I am state A and I have I can perform three different actions. I can do action 1, I can do action 2, and I can do action 3. For each of these state action combinations, I'm going to have a value associated with those state action combinations. And how do I get the value of each state action combination? It's by taking the immediate reward, right? The immediate reward. What is the reward of going from state A to state B, given that I take action 1, right? And then multiplying that by the probability that you're going from state A to state B. And you do that for all of these different actions. And that's the immediate reward. The future reward is you take what's the probability of going from this state to the next state, so from state A to state B, given that you take this action, and then multiplying it by what's the value then at being at that next state? What's the value of being at state B? So that's what we call the future reward. So when you add this immediate reward to the future reward, you get the value at each state action combination. When you take the max of all of the state action combinations, you get the value of being at that particular state. So that's the Bellman equation in a nutshell. It's calculating the value, what's the worth of you being at this particular state when you're trying to achieve some sort of reward. This is commonly used in value iteration and policy iteration and reinforcement learning when you have an agent that's trying to learn from the environment. And there's many different ways of getting to this value. One is the iteration approach. So this is the recursive process that we're able to iterate. Another is through a simulation process. We're able to simulate starting at many different states. You're able to simulate what is the discounted reward at each state given each action. And then there is a matrix inversion technique because this can be written into an explicit equation, and you can simply solve the equation using matrix inversion, and you're able to get to a particular optimal policy and a particular optimal value function. Now let's take a look at different trading mechanisms that are used. First is mean reversion. So this is the idea that asset prices will normally, over the long term, revert back to their mean. So this is an indication of whenever you see an asset, a price that's deviating from the mean, that in turn is prompting of a signal. And then another one is moving average. We talked about moving average time series modeling. It also is a technical indicator as well. So you can have a 50-day moving average versus a 200-day moving average. And the entire purpose of that is a detection of deviation from normality. Right? If we detect that this 50-day moving average is crossing over this 200-day moving average, then that we're able to send a buy or sell signal. And so that's the entire point of these technical indicators. And you never want to use one technical indicator by itself. You want to use multiple variety of indicators. Also use some market data. Also use some news sentiment. You want to have a variety of different indicators you're using to create a decision. You never want to only use uh, one indicator because you want to have these multiple different sources. And now let's take a look at some of the LeetCode style questions have come up with regarding strings. So one of the questions that you can make is what letters are the farthest from each other in this given string? And so farthest can mean in terms of in the alphabet. Farthest could mean in terms of from a specific letter in the alphabet. Farthest could mean, so, and these are just two different definitions. You can create multiple different definitions of what distance actually means uh, in terms of what letters are the farthest apart or the closest. You can define many different definitions of distance. So we just talked about two here, the alphabet for distance from Z or distance from A, and then distance from a certain letter. And then you can also represent these numerically, right? Numerically, and then you can think of these as, okay, maybe distance to the next prime number, right? So there's so many different ways you can think of this distance. And then second one is what clusters of letters that are close to each other. So can we form clusters, or what is another way you can think of it is what combinations of three letters or what combination of three letters forms the closest cluster? What combinations of three letters form the closest cluster? So these are a few LeetCode style questions that could arise. So that's it for this. See you in the next one.